Okay, so today we will start or continue with the third lecture here of antenna technology. Before I start, I should also say that if some of you have not signed up for the FECO license that we sent to them, do it now before the break and I can add them to the list. So we can also supply your name and email address, and that you do on the Canvas page. Okay, so then we should start with today's lecture. And what we will do today is that we continue on where we were last week. So last week we start looking at this thing of getting the radiation from simple antennas. And what we did is that we said that we knew the current on them, which means it's typically like dipole antennas or simple antennas where we have an idea of what the current distribution is. And then we showed how we can compute the far field from the antennas. So we could get this radiated field from the antenna. What is the field outside of the antenna? And typically what we calculated was the far field, so the radiation pattern of the antenna. And from this we can determine directivity and so on for the antenna. So very many important parameters. And this is really one of the fundamental things in antennas, and one of the things you should know in this course is that you go from the currents on the antenna to the radiated field. And you should know how you do this. And the basic procedure there was that you took the Fourier transform of the current density, and that gave you the radiation vector. And then you removed the radial component on that radiation vector to get the radiated far field. So that is the procedure, and you should have understand where the formula comes from. We looked at this time delay that you have from different positions of the antenna to the far field, and we also interpret these things of the normal component of the removing of the radial component of the radiation vector as these things of a plane wave which propagate with E and H perpendicular to the direction of propagation, and the direction of propagation is in the radial direction. What we will do today is that we will go to the feeding of this antenna. So now we will look at the antenna from the perspective of the circuit, what sits behind it. And that sees something which is the input impedance of the antenna. And then we can talk about matching, bandwidth, the Q factor of the antenna, and so on. So that is what we will come into today. And yeah, you can see we are basically up here, and here you have some references to the books. And then on Wednesday, we will continue with the first computer exercise. Okay, so our dipole that we've been looking at. This is a picture animation from Wikipedia. And you can see the feeling what we have done so far. That is this current I of X that you have here, which is the blue color. So something that is basically on the antenna just pumping up and down. So a lot of current, positive, and then it becomes negative, which means it goes in the opposite direction. So you can see the arrows here, they're pointing to the right, they're pointing to the left. And in the same way, it means that in one way you say it's up, or one way it says it's down. So it tries to show the same thing. The red color here shows the charge instead. So you can see it's plus charge on one side, minus charge on the other side. And this is what gives the radiation of this dipole. What we will do now is that we go down to this lower piece of it. And in this case, you just have a current moving here. So this is a transmission line which is connected to the antenna. So here you have a current, and you also have a voltage. And if you have a current and you have a voltage, you have an impedance, because the quotient between the voltage and the current is the impedance. And that means that will give the circuit quantities of this antenna. And that is really what we will focus on today. So how do we describe this? How do we connect the antenna to a cable, for example? So looking at this, we need to connect the antenna to something. And what we saw in the picture or the movie, the animation before, what's called a balanced feed or a twin wire feed. So here you can have two lines. This is the transmission line, and they have some distance, they have some radius, And a typical version in real life is what you have up here. Just two wires next to each other. So that means you can think about it that one carries a current this way, and then the current comes back here. Then, of course, you have an alternating current. So sometimes it goes this way, and then a certain time afterwards, it goes the opposite way. But then it's also changed direction on this. So these lines are in some ways equal. It's not that the upper one is different from the lower one. And that's what we also call this a balanced feed. And the dipole has the same type of symmetry, which means that this transmission line fits the dipole very well. So it has many names, this kind of wire. And what can be shown from this is that it has a characteristic impedance. So if we have a geometry like this, again, the wire radius here and the distance, the characteristic impedance of this transmission line is approximately the free space impedance, 377 ohms, divided by pi, and then the logarithm over the distance divided by the radius. And that can be calculated, this number. How we come up with that is not very important for this course. There is some discussion about it in the appendix, but it's a typical thing we get out there. And when we look at this, it has a characteristic impedance around 300 ohms. And that's due to what you have to do with the distance between this and the wires that sits there. So this is just a classical number of what this is, which means maybe it doesn't fit so well to your your dipole antenna. We will see that later. And next lecture, we will see how we can solve some problems that comes with this. And if you look at the electric field on this line, it basically goes from one side to the other. And again, you can think here that one has a positive charge, one has a negative charge. So if the current goes one way, you can think the charge would be positive, and the other way it could be negative. And in that case, you get an electric field between these two that just goes from the plus to the minus here. Very, very strong field between these two. And then outside, it is weaker. And this calls that it's balanced, which means that it's symmetry. The two wires are the same. So this is a classical line. A more common connector, and actually the connector that you will also use in the lab, in the patch antenna that you will build yourself, is an SMA connector. So this looks very different. So here you have the SMA connector. And this is a connector that is connected to a coaxial cable. The coaxial cable is what comes outside here. And you know that in the coaxial cable, you have an inner conductor and an outer conductor in some ways, like a shield around it. And the electric field is inside here. So it's between the inner conductor and the outer conductor here. And if you compare with the twin wire, here you can see that these are different. This connector here is very different, or the line here is very different from the line here. They are not the same. And that means this will be unbalanced. But this is a classical connector for these coaxial cables. And a characteristic impedance for this are typically 50 ohm. And that is one of the reasons why everything is 50 ohm. So the world has in some ways agreed that it's good to make cables 50 ohm. It's good to make measurement equipment 50 ohm, which means that in many cases, it's good to make antennas 50 ohm. So when we design antennas, we typically try to make them 50 ohm. And a big reason for this is that all cables and all measurement equipment are 50 ohm. Sometimes it's a huge advantage to make your antenna something else than 50 ohm. And in those cases, yeah, we just have to use another impedance. There's nothing that says that fundamentally it should be 50 ohm, except the measurement equipment and the cables. So today, in many cases, you actually try to put your amplifiers very close to the antenna, and then you don't put the coaxial cable between them. And then you are not restricted by this 50 ohm in the same way as you are usually when you have the transmission line or cable. The cable here, or this SMA connector, typically works for up to 18 gigahertz, but there are versions for higher frequencies. And when you go up in frequency here, you typically pay a price that it gets more sensitive. Everything gets smaller because the frequency is higher, so the wavelength is shorter, and the losses are higher in them too. Many things happen there, but there are versions of these connectors for almost any frequency range you would like. at least up to 100 gigahertz approximately. They start to be incredibly expensive. In the lab, when you use this, you will also learn that these are quite sensitive, so you have to be rather careful when you connect them to your antenna. So it's a sensitive, and in some cases, especially higher frequencies, rather expensive device. If we look at the electric field between these two, it typically goes from the inner conductor to the outer conductor here. Could go the opposite way too, but it goes in the radial direction around this inner conductor. So very, very different from this twin wire that we had before. And this is an unbalanced transmission line, which means that the connector here or cable, this one inner one and the exterior one are very different. They are not the same. There is no symmetry between them. And when you connect these to your dipole antenna, you need something called a balloon, which is a transformer between something that is balanced, which is the dipole, and unbalanced, which is your SMA connector and coaxial cable. So that needs to be attached when you go with these two. Something needs to transform them. So these are the typical connectors that we have. And those are something that you, of course, need to take care of. You need to know how they work. And especially you need to know that the antenna can really fit together with this type of connectors and cables. So we need to adapt to that. And the big thing is really this one here. You have here your characteristic impedance that is 50 ohm, which means that we would like to make our antennas 50 ohm. So we need to talk about what do we mean by the antenna being 50 ohm. How do we model this? How do we model our antenna as a circuit in some ways? What is a circuit perspective of our antennas? And when we start looking at that, we can start thinking about the transmitting antenna. And if you have a transmitting antenna, you typically have some electronics here, which generate and amplify some signals. So that is what sits behind here. So somewhere here, there is some electronic equipment that can produce the signals you want to send. It might be that those sits slightly behind, and this is just amplifying them, for example, in the end. And then they are processed before. And then we say that these are sent over a transmission line with the characteristic impedance at Z0, and then it goes out to your antenna, and your antenna starts to radiate. And what we would like to have is, of course, a circuit model of this one. So we would like to make this to a classical circuit that we can analyze. The transmission line here can be a twin wire, coaxial cable. It could be a waveguide. I haven't shown a waveguide so far. It's a different type of transmission line. And that is what connects here the electronics with the antenna. So we have this as an interface. And that is in the majority of type of antennas. It starts to change, especially in some cases where we actually put the amplifiers, as I mentioned, really almost on inside of the antenna. We try to merge them in some cases. But here we have one way where we say we generate them, they propagate in the transmission line, and then they go out here. And we know very well what the electromagnetic fields are on the transmission line, and that is what we use. And then the antenna, of course, transforms the signals on the transmission line because it creates currents on the antenna, and these currents creates this radiated field. So to make a model out of this, we use what's called this Thevenin equivalent to model the electronics. And I think that is something that all of you recognize from your basic electronics courses, that a source, typically like a battery or something, could be modeled with some voltage, V0, so the Thevenin voltage, and some internal resistor that sits here, which now is then some R0. So that is our model of the electronics. And since it comes out two cables from the electronics, yeah, in circuit theory, we know it can be modeled like this. It can also be a Norton equivalent, but we start with the Thevenin. And then afterwards, these two wires from the amplifier is connected to the transmission line with the characteristic impedance Z0. And then we say that the antenna sits here. And now you can see, I don't care at all about currents on the antenna, radiated electromagnetic fields. I only say one thing, and that is that our antenna has some input impedance here I call ZA. So from the circuit perspective, the antenna is just an impedance. And that is the impedance I need to know if I'm going to design the electronics that sits on the other side of the antenna. That's basically the only thing I need to know in these cases. So that means I need to say, what is this one? How do we interpret this input impedance of the antenna? That's what we need to know from the antenna point of view. So what we now want is, of course, that the signals that comes from the amplifier, so they come out here on the transmission line, they should just continue here and they should radiate. I don't want them to come here, hit the antenna, and get reflected back. And to make sure here that very little small part of the signal is reflected back, I need to look at what's called the reflection coefficient, which measures how much of the signal that comes here gets reflected back. That is reflection coefficient. And that is given by the input impedance of the antenna minus the characteristic impedance divided by the sum of the two. And if nothing should be radiated back, it means that these two reflection coefficients should be 0. And that means that this ZA should be equal to Z0. So if my antenna has an input impedance equal to the characteristic impedance, typically 50 ohm, nothing is reflected back. And that's where I would like to be, because that means that the signal that comes from the amplifier goes on the transmission line and then gets radiated out. There might be losses in the antenna, and then some of it is heating. But it's really accepted by the antenna, the parts of the signal on transmission line. So to do this, of course, you need your ZA to beat Z0, typically 50 ohm. And in some cases, actually a fraction of this electromagnetic signals is reflected back towards the antenna. So if some of this is reflected back, so a reflection coefficient is not 0, then something could happen. So here you could create different things. So what do you think will happen or can happen if these cases is not matched? So your reflection coefficient in these cases is not 0. What will happen in that cases? So I have some options here. Either you can get a reduction of the transmitted power, you can get distortions of the transmitted signals, and you can get power reflected back to the amplifier. So what can happen in these cases? So either one or more answers could be correct here. So we will try this as one of these polls again, and then we will discuss these ones. So remember here what A, B, and C are in these cases, and which one you think is correct, or which ones, it might be more than one. And then answer this poll when I start it in a few seconds. And then we will actually discuss what is happening when you have a reflection coefficient, which is not 0 in these cases. So we start this once, we take a few seconds to fill it out. So remember what A, B, and C are, because they will disappear when I launch this one. So take and fill out this poll, and then we will continue in a couple of seconds. Okay, we're up to 50% has voted now. So okay, very good. I will close it. We're almost up to 100% now. So you can see the results here. A, B, and C received 88, 76, and 94%. So C won, but basically all of them won. And in this case, actually all of them are correct. So what's happened here, and what you can see in this is, of course, if some of the signal is reflected back, of course, you lose that power in your transmission. So if you think that reflection coefficient, it measures how much of the signal is coming to your antenna. So basically in the antenna here, you have your signal coming into it. So signal is coming there, and you ask how much is coming back. And that one, if this one is now some E in there, then what goes back is gamma times E in. That is what is reflected. And the power that is reflected back is in some ways proportional to this gamma squared. So if I take the square of the signal, I get something that really is the power. You square the voltage, some normalization constant. And that means you have to square the reflection coefficient. So that measure, you lose that power. And you don't want to lose power. So that's correct. B was also correct. You get distortions of the transmitted signals. So why do you get distortions of these signals? Quite a few answered correct on that one. So can somebody enlighten me? Why is this correct? Why does it create distortions of the signals, or can create distortions of the signals? Is it some of you who has some idea why this happens or can happen?
Maybe the power which was like transmitted is not much, and due to that at the receiver side, the receiver has not received all the information. So is that what you are calling as distortion?
No. So that is really that you get a lower power level. So that is really A in these cases. So you get a lower level because some is reflected back. Distortion, I mean more that the shape is changed. So if you think you would like to send something, let's take the simplest case, you send like a pulse or something. Then on the outside, you don't get a nice pulse. If you have some communication schedule, you have some modulation and coding on it, you get not the same signal, it gets slightly different, that signal. So it's changed its shape in some ways. That is what I mean with distortion in these cases. So why do we get something like that? Why would it change the shape of it? So what happens in these cases? Again, now, imagine here you get a signal that is reflected back. What will happen with that signal? That will, of course, go to your amplifier. And imagine now that you have a case that your amplifier is not now perfectly matched to this one, which happens quite often. What will happen with that one when it hits the amplifier? It's get reflected again. And then it gets reflected towards the antenna again, and it gets reflected again, and it starts bouncing forward and back on this line. So what you will have there is in some ways that you have your transmission line here. You have a signal that comes in here. It gets reflected back here, and that is again this gamma EI, if I have this one. But then here you have a new reflection coefficient. So if this one is gamma, then you have gamma amplifier there. And then it gets reflected there again. And then, of course, afterwards, it can get reflected back again and forward and back here. So you can get a signal that goes forward and back on this transmission line. And then it takes a certain time to move from the antenna to the amplifier. Not a lot of time, because the signal is very, very fast. But it takes some time, which means that the reflected back and the reflected out again will be a slightly time-delayed version of the first signal. So you send your original signal, and then overlaid of that, you get a signal with lower amplitude and a little bit time delayed. And that is one of the effects you can have. Of course, if you make a perfectly matched amplifier, you don't really get this. But you can have that part if both of them are mismatched. So that is one of the effects that can come there. C was, of course, also correct, since A is correct, that you have power that goes back to it. And in some cases, this can actually create problem, because it can load the amplifier in a way you don't want to have the amplifier to be loaded. And this is typically in cases where you need to transmit high power levels. So if you sit in applications where you really need to transmit a lot of power, it's more important that the antennas are matched. It gets more important in those cases. So, as I said, yeah, you have a waste of power, basically. This is what's transmitted. So the power in times this number, 1 minus reflection coefficient squared. You can get problems with electronics if you send back a lot of power to it. It's most modern cases, it doesn't really happen, but it can happen. And you can get these distortions here due to this time delay of ways waves that are reflected forward and back on the antenna, and it's typically called ringing on these lines. So if you have cables which are not matched perfectly, so both of them are not matched, a signal will start bouncing there. And then you get an add-on on these with slightly time delayed signals. And that's, of course, you don't want to have. So again, it's important to match the antennas. If we can do it, we should definitely do it. And to match them, this is the condition that you need. This is really the important condition there. And almost in all applications, this is 50 ohms. There are applications where this is 100 ohms and so on. You can change it, but in most of them, it's really 50 ohms. It's a typical one that sits there. And this is what it can look like. So if you have, in these cases, a reflection coefficient that is 0.5, you can see the total voltage here on the transmission line coming out here. So this would be a coaxial cable, this twin wire or something, and you get a superposition of the incoming wave and the reflected wave. And you can see that the amplitude is going up and down. And that's because sometimes the peaks are at the same place, and sometimes they are not at the same one. So constructive destructive interference. You can divide this as this incoming wave and the reflected wave, and the incoming now is this red one and the reflected one is the green one. And you can see that the amplitude of the reflected one is now half of the incoming one, and that's because the reflection coefficient here was 0.5. If I now make the reflection coefficient better, so I reduce the level of it here to 0.2, you can still see that the signal go a little bit up and down. Sometimes this is called a standing wave ratio. And if you look here, the reflected one is now much weaker. And this is now the amplitude. So the reflection coefficient measures how much of the amplitude is reflected back. If I take the power, I have to take it square, this number. So it's less in power and some less comes back. But these are the reflection coefficients that we have. So now we had the transmitting antenna. And of course, when we had our transmitting, we have to go to the receiving one. And in the receiving antenna, we could make a similar model here. Now we should transform the incoming EM wave to an EM wave on the transmission line. And again, the transmission line can be almost anything here. And if we put up a model for this, we do a similar thing that sits here. We have an incoming signal on this side now. It comes to the antenna goes to the transmission line, and now I should just receive it, which means I don't have an amplifier now at the receiving side. I just say that I receive the power. So I can model that with only a resistor that sits there. So think again, Thevenin equivalent, but you turn off the voltage. And if you put up a model for this, then you can have a Thevenin equivalent now on this side instead. So you have your inner impedance of your Thevenin equivalent, which is the input impedance of the antenna. You have some voltage, which models the signal that comes in, and this is connected to a coaxial cable again. And you have the same thing here again, that to get the maximum received power, we need to match this transmission line with the antenna. And now you should, of course, have maximum received power, or maybe even better, maximum signal to noise ratio. So that is what we would like to have. And as the same way as before, to avoid multiple reflections, this ringing that comes, we should, of course, match everything here. So in the best case, this one is basically matched to this one, and we can also match it to the antenna that sits there. So all of them are matched to each other. That's what we would like to have. But in some cases, you actually design for other type of parameters. So a similar model for receiving antennas. And by reciprocity, we now have the same behavior for this. So everything is reciprocal in these antenna systems. It's not really true in general, because if we dig out into the electronics, there are pieces where we don't have reciprocity, which you typically have some magnets and so on that sits there. And something in the electronics, sometimes is not reciprocal. And then actually the antenna can behave different in transmission and receiving. In this course, everything will behave the same. And that means that we really have the same model. So transmitting signal, transmission line, antenna radiating, receiving signal in, transmission line, received signal. So they are the same. And if we do that, we can see that to determine both the receiving properties and transmitting properties, the only thing we need to know is this input impedance of the antenna. So the circuit characterization of the antenna is really this input impedance that gives us what we would like to have for the antenna. And having it, as I mentioned before, we have the reflection coefficient. And that means that in a transmitting antenna, we get some reflected power on transmission line, which is the incident power here times the reflection coefficient squared. That says how much power goes back. And if we think about numbers now, because numbers actually gets important in these cases. So a typical value on the reflection coefficient, when we try to make an antenna to it, it's a value of 1/3. That's a typical number that we try to use in some ways. And what that means is that then the power that gets reflected back is the square of these ones. And if you square this, it's almost like 1/10, because 3 to the power 2 is 9, and 1/9 is approximately 1/10. So the reflection coefficient squared is approximately here 0.1. And that means that 1 minus these ones is 0.9. And that is what you have in the accepted power of the antenna. So if you have a reflection coefficient here, which we will see then when you match it, when you make your own patch antenna, you will try to get a reflection coefficient of 1/3, so 0.33. And that means that the accepted power of the antenna is 90% of the power. So you approximately have 90% of the power coming to the antenna is accepted by an antenna, which is a fair number. At the same time, you can say, this is good. I actually lose 10%. And that's typically what you have to do. There are many cases where you actually have to lose even more. So power is wasted in many of these situations, that's it. And it's kind of unavoidable. You cannot have a perfect match for all frequencies. You can have it at one frequency, but you know that every system we have works over a bandwidth, and there will be mismatch over that bandwidth. And a typical cellular phone don't even operate here, maybe at 0.2 instead. And that's of course makes this even less power. But it's not as bad as it looks when you see 1/3, because the power is of course squared of this. So it's not terrible in some ways. And yeah, that means that the radiation intensity in this case is of course the incident power on the line, 1 minus reflection coefficient squared, and then the gain, and then normalization of 4 pi. That is radiation intensity. So what we see is that we can lose a little bit of this. So the mismatch we lose there. And if we have a receiving antenna, exactly the same thing. We get the same loss of power here, 1 minus reflection coefficient squared. And here we have to use the effective area and the incident power density. And then we get the received power on the transmission line, which the electronics then afterwards should take care of. And we only in this course care about this interface to the transmission line. What's happening with amplifiers, yeah, that you can do in other courses. Now comes a very common misconception with this. And it's very often actually said that half of the power is lost in these cases. It's extremely common, and it can happen in some cases, but it doesn't have to happen in these cases. So if you assume now that your antenna is matched to the transmission line, exactly what I said we would like to have. So we say that the antenna characteristic impedance is 50 ohm, characteristic impedance for transmission line is 50 ohm. And then we model this, we can say that it looks like this model, or it can look like this model. So I can now either make a Thevenin equivalent, or I can make a Norton equivalent. And if we will take the Thevenin equivalent here, and we say that R0 is equal to Z0, 50 ohm each, of course the power dissipated here is the same power as dissipated here, which means that half the power should be burnt in your electronics. But that doesn't have to happen. And of course, you don't design your systems, you lose half the power there. You design it not to do that. And you could then think, okay, but maybe anyway, it has to be this in some way. If I change parameters here, then do the equivalent and use a Norton equivalent. Now this should be probably drawn down here. So this is the voltage source, which is V0 over R0. And if I do now the same thing with the Norton equivalent, now these are in parallel, I can compute what is the received power or absorbed power in the resistor there, and what is the power in the elements that sits here in this case. I can take the quotient between them. And if I do that, I can see that for the case here of the Thevenin equivalent, I have the values that I can see in these cases. And if I do it with the Norton equivalent, I change this. So here I have to change what the power is in the load. And then I can take the quotient between them. And you can see that they are actually different. So if these are not the same, these two, you have different values if you use a Thevenin and Norton equivalence, and both are of course equivalent. And the only thing this says is that this model is not valid for this case. Thevenin and Norton equivalents are never valid when we look inside of the source. They only are valid outside of the source. And this actually exists in many cases of literature and so on, that this is claimed, and that is not really always true. And in most cases, you don't design it for this, and then it's not true anymore. So we have to be a little bit careful there. You can look at this in the lecture notes. Of course, it also hits comics in these cases, Thevenin and Norton equivalents. I will not go through that here. So. Okay, so that is the models that we have of these antennas. So now we will look at these parameters. So for example, the input impedance. And we will look at this for our antennas. So what we have said now is that we take our antenna and we basically remove the transmission line, and we replace everything that happens with electronics with the input impedance. So it's said here, which means that I should divide here the voltage over the gap with the current that's passing the gap. That should give me the input impedance. So that gives me the model I can use for the electronics. Because of course, when I go to the antenna, I still have this current that sits outside here. I have that one. I have to deal with that one, but I have to use that current to compute these parameters I need for the circuits. So we again assume we have a current that sits here. So we have a current density of the antenna. And later on, we can do numerical calculations to validate it. And the boundary conditions again says basically that the current should be zero out here at the end. Hence that's what we have. And the input impedance, the voltage divided by the current, and the current here is evaluated in the feed point. So the voltage goes over the gap and the current is passing this gap. That will give me my input impedance. And in reality, you can see it is kind of a gap here. So you can wonder what kind of current can pass this gap. But if you know from your electronics and your circuit theory, for example, think about a capacitor. The current can pass a capacitor. A capacitor is also a gap that sits there. And now we are driving these antennas at high frequencies, so it can jump over these gaps that sits there. And of course, in reality, there is a transmission line that comes in these cases. So we will now see what this looks like. So we will take our circuit model, which means this is the antenna, and we only have the input impedance, which means the voltage over the current. And in these cases, it's typical to divide it into its real part and its imaginary part. So we divide the input impedance as real part, imaginary part, and that is of course the resistivity and the reactance of this input impedance. And we can compute the complex power that we get here, because that is the voltage times the current and the complex conjugate. And if I rewrite this with this input impedance, I can see the complex power here, it's Z times the I squared. So one gives a real valued power and one gives imaginary power, and that's active power and reactive power. So this one gives the active power and this gets reactive power. The same interpretation as in circuits for antennas. And the resistance R is always positive, and that represents dissipation of power. And dissipation of power now can be two things. From the circuit side, you can have radiation of waves, but you can also have ohmic losses. And if you think about it, can you see the difference between these two if you see it from the circuit? Do you have any idea if your antenna radiates or if it just absorbs power? From the circuit, you cannot see the difference. There is no difference between this because the circuit doesn't see the radiation. It only sees is something reflected back to me. So it cannot distinguish these two. So that distinction we have to make in some ways. And a typical view of this is for a dipole antenna. Here you have this R part that sits there. That is the R. And the X is the one that was below in these cases here. So this is the X that sits down. So you can see X is both positive and negative. R is always positive. So the resistance here is always positive. And those are the parameters that we have to deal with. So the X here, as I said, represent then reactive power of reactance here. And at the resonance frequency, so the first case here, very important case where you would like to be, then this one is 0. That is what you have down there. That's your resonance. Then X is equal to 0. And if X is positive, as you are here in this range, this is inductive. And down here, it's instead capacitive because X is negative. So if you think now for 1 second, why is the antenna capacitive when you sit down here? Go back to what I said in the previous one. You have a dipole, you have a gap. I said the current can pass it. It looks like a capacitor. A capacitor here have a negative reactance in these cases. So X is negative for the capacitance. So it happens at these lower frequencies where everything actually looks like a circuit. And then you can determine the reflection coefficient from these ones. So the reflection coefficient, of course, that was Z minus Z0. So ZA, I called it before, now I just call it Z here. I can write it with the real part and the imaginary part here. So R and X, I just put it in. And then I can take the reflected power. I have to square this one. And if I'm going to square this, I square the real part, I square the imaginary part, square the real part, square the imaginary part. So here I have the value of the reflection coefficient. We can immediately see this is always less than equal to 1. So this reflection coefficient is sometimes called S parameters. So this will be like S11 if you've seen it in other courses. And you can see here in the top here, we have the difference, and here we have the sum. And for the imaginary part, it looks the same. It's always plus this 1x, x squared. So that is my reflection coefficient squared, which means how much power comes back. And now what I would like to do is, of course, to make this one as small as possible. So the accepted power is 1 minus these ones. And if I would like to have my reflection coefficient equal to 0, what does that mean? It means this one have to be 0. So this is 0. So the antenna is matched. And the next thing here is that X here is equal to 0. So these are my requirements. So for the antenna to not reflect anything back, your R part, this resistive part, have to be equal to 50 ohm if your transmission line is 50 ohm. And the reactance has to be 0, which means the antenna has to be resonant. So those are the two conditions that we have. Resonance and equal resistance. And to determine this input impedance, you can do it in different ways. You can, for example, measure it. So you can measure it with a network analyzer, like down here. And this is, again, what you will do in the lab. There you will measure this with a network analyzer. So you will use it for your patch antenna. We can use numerical simulations. And in FECO, you will use this method of moments code. There are also MATLAB scripts in Orphanidis, and they're also in these lecture notes, where you can run this in MATLAB. And for some cases, we can use analytical results from assumed current distributions. And we will use that for the radiation resistance. I will show you how to do that today. So those are the 3 different approaches. And right now we will do this one during the lecture. And the next one lab, and this one, of course, also in the computer. So before we take the break, we will just show what resonance is now for these cases and how we interpret the resonance. So this is the same picture as I showed you before. So here we have the dipole, and the dimensions of the dipole is up here. So you can see the dipole have a length L. It's a very, very thin dipole, so the width here is 0.01. It's a strip, so very thin one. And then when we sweep the L over lambda, so now I normalize it with lambda. So it's half a wavelength here. Here you can see L over lambda is 0.5. And then of course it goes up. Here is 1 wavelength long, and here is 1.5. And here you can see that when it's very short in terms of wavelengths, the real part is very low. When you then go up, eventually here you get a very high value. You can see outside here, this is like 1500 ohms, so very, very high value. And then it starts going down again, and then it goes up again. If you instead follow the reactance, it goes from this part up here, it goes through resonance, then it goes down, and then it goes up again, and it gets a second resonance there, and here it goes through 0 again. So it follows this one. And then what I've drawn down here is what the currents looks like. So on this dipole, when it's very, very low frequencies, the current looks like this triangular shape. When you start moving towards half a wavelength, it gets this cosine shape. And then when you hit the point in the middle here, so when you go to this point here, it looks like more like this one here. Can you imagine why? So if you think again, now what I'm plotted is the current density. It's just a sketch of it. You have a very high resistance. And what is the resistance or the impedance in this case? Yeah, that was the voltage divided by the current. And if that should be a high value, of course, the current here in the feed should be very low. You divide with a very low number, and then you get a very, very high impedance. And then when you make it even longer, it starts fitting like more and more oscillations here of your antenna, and then you can start come up to another resonance, basically the peak that sits there. So that is a sketch of these ones. And I will just go through this like 2 minutes more before they take the break. So if we look at these ones, we can see here that we have a low resistance for the first one, as I mentioned. The input impedance is capacitive for very low frequencies, or L over lambda here is a small number, so long wavelengths. And that means that it is this circuit part. So you have metal here, you have metal here, you have a gap between them. That is a capacitor. So your antenna has to work like a capacitor. Then around half a wavelength, you start getting resonances. So you have a resonance at half a wavelength, approximately 1.5 wavelengths, and so on. And between those, you have the anti-resonances, where you have a small current, which means you have a large resistance there. So this is an interpretation what is happening here with these currents that sits there. And with that, we will make a second quiz just before the break. So the question here is now, if you have an antenna, you would like to have an antenna for 1 gigahertz, how long should the dipole antenna be? Should it be 10 centimeters, 14 centimeters, 15 centimeters, 24 centimeters, or 30 centimeters? So what we need to know is, of course, the wavelengths. And I told you before, you should know one number by heart. 1 gigahertz is 30 centimeters. That is the wavelengths that you have for 1 gigahertz. And of course, from that, you can calculate what L over lambda is. So it's 0.33, 47, 0.5, 0.8, and 1. So now remember A, B, C, D, E. I will make a final poll, and I will then explain it, and then we'll take a break. So which one do you think it is in these cases? So take and fill out here which one you think it should be. So A was 0.33, B 0.47, C half a wavelength 0.5, D 0.8, and E 1. Just fill out which one you think it should be in these cases. Okay, 52% voted. A few more. Which one do you think it should be? Okay, I will end the poll. And here you can see the result. So the majority wanted to have C, which is 0.5. Quite a few also B, and then some people thought A, and some people thought E. And if we go back to this one, in these cases, so A, that means that you will be sitting at 0.33. You are down there. Not very good. Radiation resistance very low. The antenna is not matched. Very strong imaginary parts. If you go to B, you would go here. You are at the resonance at the antenna. You still have a radiation resistance. If you go to C, you are sitting up here, 0.5. Okay, I couldn't draw it precisely. So that means that you have some radiation resistance and you have also reactance, positive reactance, so it's inductive. At 24, you are up here. That is D. And of course, E is somewhere here, a wavelength. So what is the answer of this? Of course, depends what you should like to do with it also. Oh. You should have it 47 if you would like your antenna to be resonant. So in dipoles, I know the most famous dipole is the half wavelength dipole. The half wavelength dipole is incredibly good, but actually you don't design it to be half a wavelength. It's approximate. You design your antenna to be resonant. You would like it to be resonant. And the resonance is slightly below. It's a little bit shorter. That is typically what's happening. There is nothing that says that half a wavelength dipoles are perfect. They are a really good thing, but they are not really half a wavelength. They are slightly off from it. And that is something that we, of course, need to know in these cases. Okay, we will continue with resonance after the break. I'm sorry I drew over there a few minutes, so I will stop here.